Hi, my name is Jaewon at Seoul National University, South Korea. In this paper, we propose a deep neural network inference system for videos on mobile devices. All in one slide, our system ShadowTutor is in the context of helping a mobile device perform DNN inference. The problem we focus on is that significant network traffic is incurred by naively offloading computation to the server. And we solve this by distilling knowledge of a large teacher network to the mobile device across the network. Compared with naive offloading, ShadowTutor reduces network data transfer by 95% on average and increases throughput by over threefold. The rest of this video will walk you through the motivation and design of ShadowTutor, followed by experimental validation. Through recent years, deep learning has proved to be effective for various tasks. As a natural course, DNNs became one of the most important components that drive application performance on mobile devices, and many of these include processing videos shot from the mobile device's camera. There are two major approaches for mobile DNN inference. The first is to build neural networks targeted specifically to mobile devices, which include the famous study by Google, the MobileNet. The second is to develop frameworks that upload the unwieldy computation load to powerful servers and retrieve the results. For this approach, the server can be the cloud or a nearby edge server, such as a cloudlet. Both approaches have advantages and limitations. Since the on-device approach does everything on the mobile device, there is no server workload. But the on-device model is a lot less accurate and cannot adapt itself to the data distribution it encounters. On the other hand, the offloading approach allows the system to directly employ large but high-quality DNNs, but it suffers high network traffic and server load. Also, even though mobile devices are becoming quite computationally capable recently, it serves almost no part in producing the inference result in the offloading scheme. In fact, things get worse for video data, which is our primary workload. Thinking of offloading, the communication of every single frame between the server and the client incurs unacceptable network traffic. This property renders the entire system susceptible to adverse network conditions such as congestion, which is quite frequent for mobile devices. During service, this will result in laggy inference streams and fluctuations in the FPS. Under this observation, we decide to find a way to exploit the temporal coherence inherent in video frames. Simply put, frames that are temporally nearby just look similar. They share objects, movement speeds, ambience, and everything else. Thus, if we can somehow do well on one frame, doing well on frames nearby is virtually free. All in all, our aim is to find a way to enjoy the best of both worlds. That is, we wanted little network traffic and server load, while matching the accuracy and generalization of a large model. Also, it would be great if we could adapt our model to the current data at hand, and reasonably leverage the computation power of mobile devices too. There's gonna be a reason I'm saying this, right? ShadowTutor achieves all these goals and does some more. Great, so before we get into the specifics of ShadowTutor, I'll provide a brief overview of the technique knowledge distillation. Put simply, knowledge distillation is a technique that trains a small student model by viewing the output of a large teacher model as the label of the input data point. See in the figure that we want to classify X as an elephant. We run both the teacher and the student with X, and train the student by reviewing the output of the teacher as our label. Also, notice that this is test time, not training time. That's why we don't have the ground truth label for X. Since ShadowTutor is an inference system, it'll never get access to the ground truth label of the video at hand. It is of course possible to learn from the ground truth label if we have access to it, but this is not the case, so we only learn from the output of the teacher. Now let's get into ShadowTutor. As mentioned before, ShadowTutor is a system for video DNN inference. The video is generated on the mobile device, and the frames are processed one by one in strict temporal order. That means once the frame has been processed, it can be readily discarded. Decided by the keyframe striding algorithm, if the current frame is a non-keyframe, its inference is handled entirely on device by the student model. Otherwise, if the current frame is a keyframe, we send it to the server. Upon keyframe receive, the server updates a copy of the student model using knowledge distillation and returns the updated weights and the accuracy of the updated student. Now the updated student model can handle the inference of the keyframe on device. The distance to the next keyframe is determined by the keyframe striding algorithm using the performance of the updated student model. In the overview, we have abstracted away two important components, that is, the knowledge distillation algorithm and the keyframe striding algorithm. Knowledge distillation, or student training, is a thresholded early stopping algorithm with the maximum number of optimization steps given. In other words, we repeat optimization steps until either the student has reached a certain accuracy or if the maximum number of updates has been reached. Next, the keyframe striding algorithm outputs the stride to the next keyframe given the current keyframe stride and the updated student's accuracy. It is important that the stride takes the student's performance into account, while being also computationally simple enough to execute, because ShadowTutor is a latency-sensitive system. Although there are existing literature in keyframe striding, we find most of them inappropriate for ShadowTutor, thus we developed an adaptive but also simple heuristic algorithm. Refer to the paper for the exact algorithm. In addition to the utilization of temporal coherence and knowledge distillation, we incorporate two optimizations that will suit ShadowTutor. The first is partial knowledge distillation, where we update only a subset of the student's parameters. This reduces the time for distillation and the amount of data transferred between the server and the client. Also, surprisingly, partial distillation generally improves the accuracy of the student. Also, on the client side, we implemented asynchronous inference, where the client doesn't sit waiting for the updated parameters to arrive. Rather, it just proceeds on to the next non-keyframe. This is the key mechanism that allows ShadowTutor to be extremely robust to adverse network conditions. Finally, we derived analytic models for the throughput and network traffic of ShadowTutor. ShadowTutor has a few system configuration knobs, so these models help the system designer to estimate the performance of the system before actually implementing it. We have evaluated the accuracy of these models and found that experimental results strictly obey them. To evaluate ShadowTutor, we employed an NVIDIA Jetson Nano board as the client. The embedded board is comparable to recent mobile devices that come with fairly capable GPUs. Also, assuming strong Wi-Fi connection, we limited the uplink and downlink bandwidth of the network to 80 Mbps. The reference workload is HD video semantic segmentation. The dataset we used is called LVS, the Large Video Segmentation Dataset. We implemented the system with OpenMPI, PyTorch, and Detectron2. We have also open sourced the code at GitHub, so if there should be any unclear implementation details, you can check the code. There's a lot of numbers in the paper, but I'll go over the bottom line of each section. First, in terms of throughput, The average is around 6.5 frames per second on 720p HT videos. This is an increase greater than threefold compared with naive offloading. Network data transfer also shows a 95 reduction compared with naive offloading. Especially for the fixed camera people subject video group, ShadowTutor yields a surprising 98% reduction. The accuracy of the student model is around 72% of the teacher. It should be noted that the student's number of parameters is only 1% compared to the teacher model, and the size of the student is smaller than a single video frame. Also, neither the student nor the teacher has ever seen the input video. Next, from the original 25 FPS video, we resampled all of the frames to 7 FPS. This elongates the time difference between adjacent frames, thereby weakening temporal coherence. Yet, the accuracy only drops by 6 percentage points. By matching the input video frames per second with the average throughput of the system, we have shown the feasibility of real-time inference in actual production environments. Finally, we have tested the robustness of ShadowTutor by reducing the network bandwidth and measuring the system's throughput. As in the plot, ShadowTutor retains its throughput extremely well under low network bandwidth, while the naive offloading scheme gets hit directly by the reduction in bandwidth. Different colors for ShadowTutor represent videos with different difficulties. The easiest softball video retains the throughput even when the network bandwidth is 20 Mbps, and all of the videos quite well retain their throughput until 40 Mbps. That is half of the original network bandwidth limitation. Thanks for watching up until now. Now we'll conclude. ShadowTutor is a video DNN inference system. It incurs little network traffic and server load and matches the performance and generalization of a large model, even with a small model with its size only 1% of the teacher model. Also, we adapt the student model to the current video stream at hand through online knowledge distillation, and the computation power of mobile devices is reasonably leveraged. In addition, ShadowTutor improves throughput over 3 times and shows incredible robustness in the face of adverse network conditions. So can we enjoy the best of on-device neural networks and computation offloading? Yes, that is our claim. Thank you again for watching, and I'll see you at the online conference.